Good morning, boys and girls, and welcome. Today we are about to embark on a wonderful journey in the unit of series. I always like to start this unit with a little introduction to Taylor series, where we'll end the unit at the very end. We'll kind of come back to Taylor series, but this is what we're trying to kind of build towards and talk about. And in the middle of this, we're going to talk about some different tests on series to see whether they converge or diverge and how we can tell that. But the whole reason we're going to perform these tests is so that we can later use them on different series like Taylor-Maclaurin series. All right, so today's just going to be kind of just a quick introduction, and we're going to just talk about some series stuff and see where they come from and kind of just play around things a little bit. It's a lot of fun, and we'll see how this comes across as a video today versus live and in class. So, a little playing around the calculator today. So, without further ado, let's go ahead and get started. Alright, so up on the computer screen, generally I like to pull up my graphing calculator. I'd like to show you guys this function and have you guess what this function is. So generally, I hear a lot of people start guessing and saying, hey, that's the line y equals x. And then I have some other people, generally, because I do this earlier in the year, that kind of like, no, I'm trying to trick you. You know, maybe there's a different function, not y equals x. So let's investigate a little bit and see if it is or is not y equals x. I'm just going to trace along this graph, and we can look at our x values. When x is 0, y is 0. That's good. And we can kind of just see as I move along this, are they the same? And if you kind of look, yeah, they're pretty close. But as I get further away here, right? I don't know if I can go quickly here with this. These don't like to work well together. Oh, geez, now it's really going. Well, as we get further away, will it stop? Oh, geez. Oh, geez. Now it's going. As we get further away, this is not where I wanted to be. Stop. I don't know if I can stop it. Oh, there I can. Nope, not stopped. Oh boy, let me pause until we get this figured out. Okay, after having to force my calculator to shut down, I'm back. I fixed it. If we look here, though, at the values now, though, it is close, 0.102, 0.101, but they're not exactly the same. So we know that this is not y equals x. This has got to be some other function. Mr. Mortara must be trying to be sneaky again. Okay, so let's take a peek at our window. Oh, look how small our window is. Negative 0.24 to 0.24 and negative 1.56 to 0.156. Is that a good window look at stuff? No. We probably should move out a little bit just so we can really see what's going on. So let me fix the window and let's do that. Alright, so now I've changed our window from negative 3 to 3 on the x-axis, negative 2 to 2 on the y-axis, and now if we graph... Oh, tricky Miss Mortara. That looks like the graph of y equals sine x instead. But we had this conversation, or one very similar, when we first started about tangent line approximations and approximating functions. And how, you know, some function can be a pretty good approximator, or we get close, locally linear. You know, the tangent line's a pretty good approximator. So let's kind of graph both these functions and see where they're the same on our calculator. If we graph y equals sine x and y equals x, you can see that, again, y equals x actually is a pretty close to sine x, you know, on that short little interval. If we're talking, you know, just in that middle area, maybe between like negative 0.6 and 0.6, maybe a little less, negative 0.3 to 0.3, maybe a little tighter, you know, somewhere negative, I don't know, somewhere right around in there. Those are look to be pretty close to being the same exact line. Now, another way to look at this approximation would be to look at the difference of these two functions. We have this one in, well, let's see. Right now, we've got this one in y1, right? And we have this one in y2. So we're going to create a new function y3, and we're going to say, hey, what's y1 minus y2? All right? What is that going to look like, and what can we interpret from that? So in y3, I'm putting our new function, y1 minus y2, and we get that function there. And again, this place where they're pretty close together, you can see that that difference is near 0, right? As I get farther away, the difference gets bigger, and as I get farther away, the difference gets bigger. But right there towards the middle, that difference is pretty close to 0. All right? Now this is the part in class where I have you guys guess, well, what function, we just created a new function there, right? The y1 minus y2. What function do you think that is? And so I have you guys fetch out some guesses, but hopefully, if you're looking at this, you're thinking, hey, maybe that looks something like y equals negative x cubed. Yeah, that's a pretty good guess. Let's graph and see how close we are. All right, and then now we hit graph, and, well, we can see we're pretty close. That looks kind of close to negative x cubed there. It just needs to be widened out a little bit. So, then again, I generally have us play around with different numbers, but I'm going to kind of cut to the chase here. What happens if we divide that by 6? All right, and so usually we play and guess and check to this, but let's see what happens when I divide by 6, how close we get. All right, so now we got a new guess into y4, negative x cubed divided by 6, and here's our original function. Here is y equals x. Here is the difference between those, right? Those two approximations. And then here is our y equals negative x plus 6. And so, hey, that is a lot better. That is pretty darn close to, the original function. All right, cool. So now what can we do with that? Well, what we just said was that y3 was pretty close to y4, right? Approximately the same thing. And then I know that y3, again, the way we got that was y1 minus y2, where sine x minus x is approximately negative x cubed over 6. And then I can add x to both sides, and now I've got an even better approximation for sine of x. Instead of just using instead of just using x, let's try using x minus x cubed over 6. So now in the calculator, we've got sine x. I've got our new approximation instead of x. I've got x minus x cubed over 6, and I've turned off the difference for right now. And let's graph and see how much better our new approximation is. So there's sine x, and then here comes our new approximation. Wow, look at that. That looks a lot better, right? That is holding closer to our sine x for a little bit longer than the y equals x did. That looks to be a better approximation. Now, let's go through, like last time we said like maybe negative 0.3 to 0.3, and now this maybe is like negative 0.6 to 0.6. That interval is lengthened a little bit. Now, let's take this same thing, and let's do what we just did, and we'll do it all over again a little bit quicker. So I went back and I turned on the y1 minus y2, or difference between our two the real function and the approximation. And so now I get this function right here. And again, you can see it's a lot closer to 0, a lot longer. And now, what function does that look like? I can say, hint, it is not x to the third. All right? Oh, maybe it's x to the 5th. If we graph x to the 5th, you can see it looks same kind of shape, just a little bit tighter. So again, maybe I need to put an adjuster like we put the 6 on the x cubed. Maybe let's try dividing it by 120. All right, let's try our new adjustment, x to the 5th over 120. And here comes sine x. Here comes our approximation for sine x. Here comes the difference between those two things. And then now here comes our approximation for that difference. And again, it looks pretty darn close, right, except for at the very ends. So I think, again, x to the 5th over 120 is a pretty good approximation. And now working similarly like we did before, y1, which is sine x, minus y2, which is the x minus x cubed over 6, is pretty close to, that difference is pretty close to x to the 5th over 120. And now again, I could solve for sine x. And so sine x, a better approximation yet, might be x minus x cubed over 6 plus x to the 5th over 120. All right? And we could keep on doing this. Maybe let's just graph this one to see how close we are now to our real function. Okay, so we've got sine x now in y1. Again, our approximation, x minus x cubed over 6 plus x to the 5th over 120 in y2. Let's graph those and see how close we are. Here comes sine x. Here comes our approximation. And now look at that. Like, this polynomial is a pretty good approximation for sine x, at least on that tight line over there, like negative 1.5 to 1.5-ish. If we zoom out a little bit here, all right, I'm zooming out a little bit here. If we zoom out a little bit here, here's our sine x, and then again, next is come our approximation. We can see that the approximation is really, really good, centered near the origin there. But again, as I get farther away, then it kind of pulls off and it becomes not a very good approximator. But close to the origin, this is very, very close. And those values, if I were to plug in like 0.1, 0.2, would be very similar on both sine x and the polynomial approximation. This is what, again, we're going to get after for Taylor polynomials, is, or Taylor series, is there polynomials that approximate these transcendental functions. Now I'm going to tell you that we could keep doing this difference method and keep adding more terms the way we kind of added these first few terms here. But we would find out a pretty good approximation for sine x is x minus x cubed over 6, which is also known as 3 factorial, plus x to the 5th over 5 factorial, which is 120, minus x to the 7th over 7 factorial, plus, one more term, x to the 9th over 9 factorial. And you can kind of see you can keep this pattern going and in fact going on forever. And the longer that we do it, the more exact it'd be to the regular value of sine x. So plus dot, 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 dot. And in fact, here's the cool thing is like your calculator can't really evaluate sine of x. It doesn't know how to do that. What's programmed into your calculator is it's really evaluating this polynomial right here. And it takes out, maybe 10 terms or so. And that's as much accuracy as we're going to need for these things to be exactly the same thing. So pretty cool. Okay, I want to play around with another function here real quick. This time I'm going to show it to you. It's y equals cosine x. And if we graph that from -2 to 2, it kind of looks like that. Now we could play this same game kind of all over again, right? What does this look like? Well, hey, this looks like, y equals cosine x looks kind of like y equals 1 minus x squared. That looks like a parabola, right? Kind of ish. Shift it up 1, opening down. We could do that, and we could keep going through the same steps we did with the y1 minus y2. But that was kind of a lot of work, right? If I want another polynomial that represents this one, what's something else that we could do? There's got to be a shortcut or an easier trick for us to use. So let's use some of our calculus knowledge to see if we can get there. I know that cosine x is the derivative of sine x. So, what happens if we just go take the derivative of that polynomial we just found? What if I go and take the derivative of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial? Will that be the same thing as cosine x? If we take the derivative of x as 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial, adding one more term, minus 7x to the 6th over 7 factorial. And then I'm going to simplify my factorials here. Maybe side note real fast. Factorials, we should be aware of those things, but 5 factorial we should know means, hey, 5 times 4 times 3 times 2 times 1 times 1 times 1 times 1. There we go. Or 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. You just start at that number and you multiply by everything down below it. So if I've got, if I've got 5 over 5 factorial, the 5s would kill each other off and just leave me with 4 factorial. Or if I have 3 over 3 factorial, that would give me x squared over 2 factorial. Plus now this would be x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And so let's see now if that again is a pretty good approximation for the cosine of x. Okay, so I've entered in our new approximation and cosine of x and wow, you don't even see anything. It's that good. It is that close. Let's zoom out a little bit. I'm just going to zoom trig here. So here's cosine of x. And here comes our approximation. So it was just that close that we could not tell the difference. You can see that this is a pretty good approximation. Again, on that tight interval, close to 0. Nice. Okay, so we just learned that y equals cosine x can be approximated by that polynomial. But what if I wanted y equals cosine of 1/2 x? Could I literally just plug in like that u for all the x's? And yes. So bottom line of today's lesson is we are going to be playing around with a bunch of series, things added together, to approximate functions. That's what we're trying to drive towards. And what we're going to need to know are, do these things converge on that value, or are they going to diverge? And so we're going to come up with a bunch of tests to kind of test that. But this is just kind of a quick preview of some things that we're going to talk about through this unit. Hopefully it'll help you kind of wrap your mind around stuff as we get to be more abstract with the topics. Alright, boys and girls, hope you enjoyed this video. See you again real soon.